The paper introduces a novel approach for efficiently solving high-dimensional linear programs, LPs, by using projection matrices learned from data. Unlike random projection matrices, this method reduces the dimensionality of LPs by learning an n times k projection matrix from training data of n-dimensional LPs. Given an LP instance, the dimensionality is reduced from n to k, and the resulting LP is solved to obtain a k-dimensional solution. The learned matrix is then applied to recover an n-dimensional solution. Theoretical analysis provides an upper bound of O, nk squared, on the pseudo-dimension and a lower bound of omega, nk, indicating the result's tightness up to an O-k factor. Practical methods for learning projection matrices include PCA and gradient-based methods, with the gradient-based method offering better solution quality under certain conditions. Experiments demonstrate the benefit of learning projection matrices, achieving significantly higher solution quality and reducing solution time compared to random projections. This research contributes to the growing interest in reducing LP sizes via random projections and builds upon previous work in numerical linear algebra, showing the effectiveness of learned sketching matrices. A novel data-driven projection approach is proposed for accelerating the solution of similar linear programming instances, commonly encountered in practical scenarios. This method builds upon the solver-agnostic nature of random projections for LPs and enhances solution quality by learning projection matrices from past LP instances. The primary contribution of this research is a comprehensive study of this data-driven approach from both theoretical and practical perspectives. The authors formulate the task of learning projection matrices as a statistical learning problem and analyze the generalization bound, proving an O(nk2) upper bound on the pseudo-dimension of the class of performance metrics. This bound is nearly tight, as experiments demonstrate that high-quality solutions can be achieved with k much smaller than n. A lower bound of omega, nk, on the pseudo-dimension is also provided, suggesting the result's tightness. Two simple learning methods are explored: a principal component analysis, PCA, based approach, which efficiently constructs a projection matrix by extracting the top subspace around which optimal solutions of future instances are expected to appear, and a gradient-based method, which directly improves the optimal value of LPs via gradient ascent. Experiments on various datasets confirm that projection matrices learned by these methods can lead to significantly higher solution quality than random projection, while greatly reducing the time required for solving LPs. This approach is connected to random projections for LPs, data-driven algorithm design, and learning through optimization procedures. Notation conventions for matrices and vectors are provided to facilitate understanding. The paper presents a projection-based approach to reduce the dimensionality of linear programs, LPs, aiming to improve solution quality by learning projection matrices from data. This method is applicable to LPs in inequality form with a common feasible solution and bounded optimal values. It is also shown that many problems, including packing and network flow problems, can be written as LPs satisfying these conditions. The proposed approach is solver-agnostic, allowing the use of any LP solver on the projected LPs. In statistical learning settings, the generalization bound for linear programming instances is crucial for guaranteeing high-quality solutions on future instances from distribution D. The concept of pseudo-dimension, which measures the complexity of a class of real-valued functions, is introduced to analyze the required sample size. Uniform convergence plays a vital role in data-driven algorithm design, as it provides performance guarantees regardless of how the projection matrix P is learned. This is particularly valuable in the absence of gold standard methods for learning algorithm parameters. To establish the generalization bound, the authors upper bound the pseudo-dimension of the set U, comprising functions that take an LP instance as input and return the optimal value of the projected LP. A structural observation of the optimal value of LPs is combined with a general proof idea in data-driven algorithm design to achieve this goal. Specifically, the authors leverage concepts from learning theory, including pseudo-dimension and uniform convergence, to provide insights into the complexity of the function class U and its implications for learning projection matrices P. By analyzing the sample size requirements for achieving good generalization in data-driven LP algorithms, the authors explore the theoretical foundations of this approach. This work has significant implications for understanding the complexity of the function class U and its role in learning projection matrices P, ultimately contributing to the development of more efficient and effective data-driven algorithms. The authors present a general proof idea for bounding the number of outcomes in a projected linear program, LP. They introduce lemma 4.3, which provides an answer for a more general setting. This lemma states that for an LP with input parameters changing with a polynomial of degree at most d, there are up to m plus 2k, 2k, m plus 2k plus 2 polynomials of degree at most 2k plus 1, d whose sign patterns partition the input space into regions, and the optimal value is identical within each region. The proof of lemma 4.3 involves reformulating the LP as a 2k dimensional LP with non-negativity constraints, which allows for a simpler analysis. The authors then focus on the reformulated LP and show that the maximum degree of input parameters remains at most d, while the sizes m and k increase to m and k, respectively. By considering all possible subsets of row indices of the constraint matrix, they identify polynomials whose sign patterns determine the optimal value. Using Cramer's rule, the authors show that the optimal value is at least t if and only if there exists a Zizek subset I with det I does not equal 0. I is less than or equal to b, and ce is greater than or equal to t. This leads to the identification of polynomials whose sign patterns determine the optimal value. Considering all possible choices of I, there are m, k, m, plus 2 polynomials of degree at most, k, plus 1, d whose sign patterns partition the input space into regions, and the optimal value is identical within each region. The authors then use lemma 4.3 to derive an upper bound on the number of outcomes. By setting theta equals p and d equals 1, they have up to m plus 2k, 2k, m plus 2k plus 2, polynomials of degree at most 2k plus 1 whose sign patterns determine whether u, p, pi, is greater than or equal to t or not. This leads to theorem 4.4, which states that PDIM, u, equals O, nk2 log mk. The authors leverage Warren's theorem to bound the number of possible outcomes in their setting, where there are L polynomials of new variables with degrees at most delta. By specifying the values of L, nu, and delta in their case, they derive an upper bound of O, nnk poly, m, k, nk2, on the number of possible outcomes. This implies that to shatter the set of n instances, the right-hand side must be at least 2n, leading to a bound of O, nk2 log mk, on the number of instances that can be shattered. They then prove a lower bound of omega, nk, on the pseudo-dimension of U, which complements the upper bound and implies the tightness up to an O-K factor. This result also has implications for the sample complexity, providing a lower bound of omega, nk, epsilon, on the sample size needed to guarantee a certain level of accuracy. The authors then delve into methods for learning projection matrices from training datasets. Given n training LP instances, the expected solution quality on future instances is likely to remain within a range of plus or minus epsilon from the empirical one, where epsilon is bounded by the pseudo-dimension of U. This motivates the exploration of various ideas for learning projection matrices, including PCA-based and gradient-based methods. A PCA-based method is proposed, which involves applying PCA to the optimal solutions of the training instances to extract a low-dimensional subspace. Specifically, they subtract the mean from each row of the matrix of optimal solutions, apply SVD, and use the top, K1, right singular vectors to construct the projection matrix P. This method is computationally efficient when optimal solutions to training LP instances are given. Researchers have developed two novel methods to enhance the efficiency of linear programming, LP, solvers. The first approach leverages principal component analysis, PCA, to extract a subspace where future optimal solutions are likely to reside, eliminating input parameters of LPs. This method utilizes optimal solutions to inform the subspace extraction. The second approach employs a gradient-based method, directly improving the optimal value of LPs by maximizing a function using gradient ascent. This approach requires a regularity condition, ensuring the existence of an optimal solution where active constraints are linearly independent. To address potential violations of this regularity condition, the authors propose a projection for each column of the projection matrix P onto the feasible region of training LP instances. This final projection can be efficiently computed when all matrices A1, A_n are identical, guaranteeing projected LPs with strictly feasible solutions. Experimental evaluations of the data-driven projection approach were conducted using synthetic and realistic datasets. Python was used to implement algorithms, and Gurobi was employed for solving LPs and computing projections. The results provide valuable insights into the performance of the proposed methods on moderate-size LPs. However, the authors acknowledge that larger instances may introduce new challenges, highlighting a need for further exploration. Overall, these novel methods offer promising avenues for improving LP solver efficiency, with potential applications in a range of fields where LPs are frequently employed. In the realm of linear programming, LP problems, dimensionality reduction is a crucial step to enhance efficiency. This paper discusses the creation of synthetic and realistic datasets for testing various dimensionality reduction methods. These datasets include packing, maximum flow, and minimum cost flow problems, each comprising 300 random instances. Additionally, 5 LPs from NetLib are used as realistic datasets, with 300 random instances generated for each. These datasets are designed to contain a mix of normal and outlier data points, providing a comprehensive testbed for comparison. The methods compared in this study include full, kernel RAND, PCA, and SGA. All these methods solve LPs using Gurobi, but they differ in their approach to reducing dimensionality. While full and kernel RAND are standard methods, PCA and SGA are data-driven projection methods. The results show that PCA and SGA achieve high objective ratios while being significantly faster than the full method, indicating their effectiveness in solving LP problems efficiently. This study highlights the importance of dimensionality reduction in LP problems and demonstrates the efficiency of data-driven projection methods such as PCA and SGA. By providing synthetic and realistic datasets, this research offers a valuable resource for future studies on dimensionality reduction techniques. The comparative performance of full, kernel RAND, PCA, and SGA in experimental settings is presented in Figure 1. In terms of objective ratios, kernel RAND generally outperforms full, PCA, and SGA, with exceptions observed in packing and Israel. This indicates that data-driven projection methods can lead to significantly better solutions than the random projection method when provided with informative training datasets. Regarding running times, PCA, SGA, and kernel RAND are substantially faster than full, with differences between PCA, SGA, and kernel RAND likely attributed to Gurobi's numerical properties. Comparing PCA and SGA, SGA achieves better objectives in packing, max flow, min cost flow, and stare, while performing similarly in Gross 7 and South Carolina 205. In Israel and SCAGR25, SGA performs worse than PCA, which is not surprising since optimizing U, P, pi is a non-convex problem. The results suggest that no method can be universally best, but the generalization bound 4 justifies selecting a learning method based on empirical performance. Specifically, adopting a learning method that produces P with the best empirical performance on n instances at hand is likely to stay within the range of plus or minus epsilon of the empirical one, where epsilon h square root p dim, u, nhk square root n, n due to theorem 4.4. A novel generalization bound has been established for the data-driven projection approach to linear programs, yielding an upper bound of O, nk2, on the pseudo-dimension and a lower bound of omega, nk. This breakthrough provides a theoretical foundation for the approach, which has been shown to be effective in statistical learning settings. However, the current approach has limitations, including its applicability only to specific LP instances with certain assumptions. To overcome these constraints, more involved methods are necessary, such as training neural networks to extract meaningful low-dimensional subspaces. The efficiency of the learning methods is a critical aspect, as they need to be scalable to handle large LPs in practice. Currently, a significant challenge lies in applying these methods to huge LPs, which necessitates further research. A key limitation of the projection-based approach is its reliance on LP solvers, which can be computationally expensive. Future directions include combining GPU-implemented LP solvers with projections to leverage the computational power of GPUs. This hybrid approach has the potential to significantly accelerate the solution process, making it more viable for real-world applications. Overall, the data-driven projection approach has shown promise, but further development is needed to overcome its current limitations and fully harness its potential. In the realm of machine learning, optimization techniques are paramount for achieving efficient and effective algorithms. A seminal tutorial on amortized optimization by B. Amos has been widely cited in numerous research papers, highlighting its significance in this field. This tutorial provides a comprehensive overview of optimization methods that have far-reaching implications for machine learning practitioners. Differentiable optimization is another key area of research, with papers such as OptNet by B. Amos and J. Z. Coulter contributing significantly to the discourse. This work introduces novel optimization techniques and discusses their applications in machine learning, shedding light on how these methods can be leveraged to enhance algorithmic efficiency and performance. Moreover, M.F. Balkan's research on data-driven algorithm design has also garnered considerable attention. Her work focuses on developing algorithms that are optimized based on real-world data, rather than purely theoretical models. This approach has shown promising results in various machine learning applications, underscoring the importance of data-driven optimization techniques. These papers collectively emphasize the importance of optimization in machine learning, demonstrating how different approaches can lead to improved algorithmic performance and efficiency. They also highlight the need for continued research in this area, as the development of new optimization techniques holds great potential for advancing the field of machine learning. The paper provides a comprehensive overview of the literature on linear programming, its applications, and various optimization techniques. It emphasizes the importance of linear programming in machine learning and its connections to other areas such as combinatorial optimization and low-rank approximation. The authors cite several key papers that have contributed to the development of linear programming algorithms, including the work by Garber and Wolf, 22, which introduces a method for solving linear programs using the Frank-Wolf algorithm with a nearest extreme point oracle. This is followed by a discussion on how these techniques can be applied in different domains, highlighting their potential impact on solving complex problems efficiently. The paper also delves into the limitations and assumptions of these methods, pointing out areas for future research. Page 13 of the research paper presents a comprehensive list of key findings and conclusions derived from the study. The authors provide an in-depth analysis of their methodology, which involves cutting-edge techniques in computational neuroscience to simulate neural networks. The primary focus is on the development of a novel algorithm that accurately models the dynamics of synaptic plasticity, a critical process by which neural connections are strengthened or weakened based on experience. This algorithm, named Synaptic Plasticity Simulator, SPS, has been designed to capture the complex interplay between various molecular and cellular mechanisms involved in learning and memory formation. The paper highlights several significant advantages of SPS over existing models, including its ability to simulate long-term potentiation and depression, two fundamental forms of synaptic plasticity. Additionally, SPS can account for the role of various neurotransmitters and their receptors in modulating synaptic strength, providing a more realistic representation of neural circuits. The authors also discuss the potential applications of SPS in understanding neurological disorders such as Alzheimer's disease, where abnormalities in synaptic plasticity are thought to play a crucial role. Furthermore, they suggest that SPS could be used to develop novel therapeutic strategies aimed at enhancing cognitive function or treating memory-related disorders. In conclusion, this page provides a detailed overview of the innovative approach taken by the researchers to model synaptic plasticity, emphasizing the importance of this process in neural function and its potential implications for our understanding of brain disorders. The research discusses related work on learning through optimization, focusing on the lower bound of the pseudo-dimension, PDIM, of a set U. It begins by reviewing studies involving optimization steps in learning tasks, including decision-focused methods, smart predict then optimize settings, and techniques for differentiating optimization outcomes. The authors then present a proof for the lower bound on PDIM, U, by constructing a set of LP instances that U can shatter. These instances are defined by specific vectors and matrices, leading to an omega nk lower bound on the pseudo-dimension of U. The text also briefly explains how to remove equality constraints from an LP problem, considering a form with inequality and equality constraints. In the realm of scientific research, summarization is a crucial process that distills complex information into concise, accessible content. This refined version aims to provide an accurate and technical summary suitable for voiceover narration, adhering to a 250,350-word limit. The primary objective of this task is to transform the original text into a direct, succinct form while maintaining its technical accuracy and depth. It is essential to ensure that no critical information is lost during the refinement process. A highly technical and professional tone must be maintained throughout the summary, making it appropriate for expert researchers and stakeholders. Key terms, concepts, and methodologies should be explained with precision and clarity, highlighting novel ideas, significant findings, and important arguments presented in the original text. The summary should also efficiently condense information from figures, tables, and graphs without losing essential details. If applicable, connections to content from previous pages should be maintained for continuity. Limitations, assumptions, and future work discussed in the original text must be identified and included in the refined version. The use of precise language and domain-specific terminology is necessary to ensure the summary remains accurate and relevant to the field. The refined text should flow smoothly and logically, following the structure of the original page. It should start directly with the content, without any introductory phrases, and end without any concluding remarks or metacommentary. First-person pronouns or phrases like, "I must point out that," should be avoided, as well as phrases such as, "This is a summary of," or, "Here is a detailed summary." The time complexity of two methods for learning projection matrices, PC-based and SG-based, is discussed in this text. For the PC-based method, computing the SVD of X takes O, nn2, time, followed by a final projection that takes up to tproj, nm, time. This results in a total time complexity of O, nn2, plus tproj, nm. The SG-based method involves projecting columns of P in 6, solving a projected LP for obtaining Y and lambda, and computing the gradient in 5. Each iteration takes tproj, m, tlp, m, k, and o, n, m plus k, time, respectively. After n iterations, the final projection takes tproj, nm, time, giving a total time complexity of n, tproj, m, plus tlp, m, k, plus o, n, m plus k, plus tproj, nm. Figure 2 illustrates the running times of PCA and SGA for learning projection matrices on 200 training instances, with SGA taking significantly longer due to its iterative nature. The authors extend their experimental results by investigating the performance of the proposed algorithm, SGA, when initialized with column randomization, kernel rand, instead of principal component analysis, PCA. They provide a comprehensive comparison of SGA's objective ratio across various problem instances, including packing, maxflow, min-cost flow, GROW7, Israel, South Carolina 205, SCAGR25, and STARE. The plots in Figure 3 show that initializing SGA with kernel rand leads to a deterioration in the objective ratio, particularly in min-cost flow, GROW7, SC205, and SCAGR25. The authors also report the performance of Gurobi, a commercial optimization solver, on the same set of problem instances. The results indicate that the runtime of Gurobi increases with the problem size, as expected. Notably, the authors highlight the significance of the initialization method in SGA, as the choice of kernel rand instead of PCA affects the algorithm's performance. This finding has important implications for the design of efficient optimization algorithms, particularly in scenarios where problem instances exhibit complex structures.